KL divergence. Let us understand what is KL divergence and how is this used as a loss function. Coming to different loss functions that you would see in machine learning, KL divergence could be one loss function that is a bit tricky to understand. So in this lecture, let us go deep into this and understand what is the concept of KL divergence, and then we'll also understand how exactly the mathematical formulation for it develops. That is, whenever you understand a mathematical formula or an equation, you should understand clearly what is the logic behind it, not just the equation that you'll forget. But once you understand the logic, it will be clear in your mind. So that is what we want to do in this lecture. First, let us see what is the concept of KL divergence. What is it used for? KL divergence, what it does is, it measures how one probability distribution, let us say Q, how this probability distribution diverges from another probability distribution. Let us say you have another distribution P here. You want to see how Q diverges from P. This is what KL divergence is going to measure. So here you are going to measure how much is this divergence. You have one distribution P, another distribution Q. So how much is Q diverging from P? This is what KL divergence will measure. Another way of seeing the same thing is, the same measure can also be interpreted as the extra information that is needed to represent samples of P using a code that is optimized for Q. This is another way of seeing it. See, both are the same concept. That is, either you can say that you have one distribution P, another distribution Q. How much does Q diverge from P? This is one concept. The same thing can also be expressed as saying how much is the extra information that is needed in order to represent P using Q, right? That is, if you have samples from P, you want to use it with a code that is optimized for Q. How much extra information do you need? That is what KL divergence tells you. What we'll do is, we'll first see the mathematical formula, then we'll dive deep into it, understand this concept in detail, then we'll derive the formula and reach this particular formula. Okay, so first I want this formula to be there in your mind. Then once we complete all the derivation and everything, you should then understand, okay, we now reach the formula that we initially wrote out. So KL divergence, it can be written as KL divergence. When I write KLPQ, how you have to read this is KL divergence of Q from P. So P is the true distribution. Q is what is the newly constructed distribution, you can say. Then how much is Q diverging from P? That is what you are going to measure. So how do you read this? KL divergence of Q from P. Okay. This can be written as sigma sum over all x P of x into log P of x by Q of x. For now, just see the formula. We'll clearly explain what exactly is this, where it is coming from. This in case of discrete random variables. If it is a continuous random variable, you can't take a sum. Instead, it will be integral. So then it will be integral. It's either this, or you should write integral P of x into log P of x by Q of x dx. So both these are the formulas using which you can calculate KL divergence. Okay, one thing. What is P and Q here? P is your true probability distribution. This is the true probability distribution. P is your true distribution. What about Q? Q is the model's predicted probability distribution. This is predicted probability distribution. So first thing, you have to get this idea clear. What are we comparing? You have a model. This is your machine learning model. You are giving some input to this, using which it is going to create as output a probability distribution. So whatever model is creating, this is Q. But for this particular input set that you're giving to the model, there will be one true distribution. So you are trying to approximate that true distribution using Q. The true distribution is P, and with the input, model is trying to find out that P. So in an attempt to find out P, model will construct Q. So Q is the one that is produced by model. What do you want to do now? When you want to train this model, you should have a loss. And that loss is derived by finding out how much is Q diverging from P. Whatever be that divergence, accordingly you will calculate loss, and this loss will be back propagated in order to train the parameters of the model. So this is the idea, okay? In order to train parameters, you want this loss function. The remaining part of this lecture, we are going to discuss how is this loss function coming up? What is the logic behind this loss function, okay? So let us get into those discussions. First thing, what does it mean when KL divergence is 0? Let us say you have KL divergence of P and Q, or ideally it should be read as Q from P, okay? This is 0 whenever P is equal to Q. That is, if both distributions are exactly the same, that is only when KL divergence will become 0. So ideally KL divergence will take some positive value, and if Q is very divergent from P, that is very different from P, let us say you have Q, let us say during initial part of your training, Q will be very different from the actual true distribution, which is P. At this point, KL divergence will be very large. Then what will you do? You will backpropagate the loss. You will train the parameters of the model. Then once your training is over, slowly your KL divergence of Q from P will become smaller and smaller. It will be somewhere near to 0. Then you can say it is almost the same distribution. That is when you can say your model is having right output. Okay. So generally, okay, one more thing about KL divergence is that KL divergence is not symmetric. KL of Q from P, this is not equal to KL of P from Q. So in this case, these are not equal. There is a reason why it is not equal. That is, it is direction dependent. So it is not exactly the difference between two distributions. Instead, you have to clearly understand that P is the true distribution, Q is the distribution produced by model. Now, how much is Q divergent from P? This question is different from how much is P divergent from Q, right? So this is the situation. Next thing you have to understand is, how are we using this as a loss function in classification? Let us say you have some classification task. In that case, we'll say it is multi-class classification. Okay, there are k different classes. Each input x can belong to any of these k classes. Okay, in this case, you will have true distribution P. What will this be? This is the distribution of true label. Let us say P1, P2, etc. up to Pk. This is the true distribution. And what about the predicted distribution? We'll call it as Q. So I'm using P and Q so that it matches these notations that I'm using. Here I told you P is the true distribution, Q is the predicted distribution. So in order to match that, I'm using P and Q here. Okay. Q will be Q1, Q2 up to Qk. This is my predicted distribution. How can I write the KL divergence? At this point, I can write KL divergence of P and Q, or Q from P. This can be written as sum over all the k classes, k equal to 1 to k, k equal to 1 to k. This is the formula, okay? P of x log P of x by Q of x. In this case, it is Pk log Pk by Qk. Look at this formula closely. You'll understand something. There is a very close relation with cross entropy that we learned in previous lectures. The relation is, think about this formula. Think about this formula very clearly. What would be the situation if your true label, which is P, if that is a one hot vector? We discussed in the previous lectures, in cross entropy lectures, that true label, it will be represented as a one hot vector. That is, if you have 4 classes and let us say second class is what this model belongs to, then you will represent as 0, 1, 0, 0. Whichever is the actual class, that will have 1 and all other classes will have a value 0. If you are having one hot representation of true labels, then think what happens to this formula. In this formula, you are going to sum over all the classes, but this value of pk, it will be 1 for the true class and it will be 0 for all the other classes. Then what happens? In each of the terms, pk will be 0 for all the classes except the true class. That means only one term will remain, which is log 1 by qk. So why is this 1? Because this pk will be 1. Okay. So this log 1 by qk, where k is the true class, or I'll write here true class tc. So this means corresponding to the true class, whatever be the value of q, that will only remain. What will happen if I take q to the numerator? This can also be written as q true class raised to minus 1. And this minus 1 comes here, then it becomes minus log qtc, or the q true class. Now think back. This formula is familiar to you. This is exactly same as what we saw in case of cross entropy. So what you have to understand here is KL divergence, when used along with one hot vector, becomes the same as cross entropy. Whatever we saw in categorical cross entropy, the same thing is what you got when you use KL divergence and used one hot vector. But there is one more case. What if your labels are not one hot? That is, not just that the representation is not one hot. What I'm going to say is, instead of simply saying that it is 100% in this class and 0% in all other classes, what if you have soft labels? Soft label means something like this. That is, you will say that instead of 100% one class, maybe you would say 0.9% in the true class and maybe slight chances 0.03 here, 0.03 here, 0.04 here, something like this. If this is how your true label looks like, then what? Then how can you use scale divergence formula? So this is one important point of where we actually use scale divergence. In this case, what happens is, these terms would not cancel out like you had seen in one hot case. This will not happen. Instead what happens? Your loss will remain as sum over all the k classes from k equal to 1 to k, pk log pk by qk. So what happened here is, in case of cross entropy, categorical cross entropy, sparse categorical cross entropy, in all those cases we had seen that when you are calculating loss, only that particular term which is corresponding to true label was significant. All other terms were cancelled out. But that is not the case when you used soft labels along with KL divergence. In KL divergence, all the classes, that is irrespective of whether it is true class or if it is the other class, all of them gets involved in the loss, which means this penalizes the model for deviating from the entire target distribution and not just the correct class, right? So this is where KL divergence is different. Next thing is, one important thing here, when I wrote this formula, you might be thinking, how did I get this formula? Okay, you understood that this is the formula for KL divergence, but how did this suddenly come up? What is the logic behind this formula? This is the core part of this lecture. This is what I want you to understand clearly, where this formula comes from. There should be some logic behind from which you are deriving all these things. That is the most important part that you want to understand. So let us understand, how is this formula coming from, what is the idea behind it, and how is it getting derived. Okay, let us get into this. First thing, what are we trying to do? What is our goal when you're using KL divergence in this particular case. What you want to do is, you want to measure how much extra information, this is what we discussed initially itself, how much extra information, or you can say how much inefficiency is there when, how much inefficiency is incurred if we use one model Q in place of another model P. Or you can say, if you use this model Q in order to represent data that is actually following P, how much inefficiency is there or how much extra information is required. This is what you are actually calculating using KL divergence. So I'm repeating this again and again because this aim is from where we are going to derive this whole mathematical formula. If this aim is clear for you, you will understand the whole derivation. This is what we are trying to represent mathematically. You want to represent mathematically how much extra information is required or how much inefficiency is there when you are using a model Q instead of the actual P. That is, you are representing the data that is actually following P using another distribution Q. So how much inefficiency is there? That is what you are going to see, or how much extra information is required. First thing you want to understand here is the concept of information content. Information content this can be measured by using a very simple formula. I of x, you will call this, and it is minus log P of x. So we'll discuss on what this is. How is minus log P of x a logical mathematical formula for information content? The logic behind this is this: whenever there is an event which is having a very low probability, that is, it is a rare event. If it is a rare event, always information content in that is very high. And whenever an event is having very high probability, that is, it is a frequent event. If it is a frequent event, then information content is always low. I'll take a very simple example and explain this. Let us say there is a football match going on. There is a football match going on between India and Argentina. What you know already is, Argentina, you already know they are a very good football team. They have top class players and they are among the best in the world. What about India? India's football team is not that great. So even before the match starts, you are very sure that Argentina is going to win this, which means you would say probability of Argentina winning this match is very high. Maybe 0.95 is the probability that Argentina will win this match, and very less probability is there that India will win this match. Then let us say you miss this match. Then in the evening a friend is coming to you and he is telling you, do you know Argentina won today's match? Did you get any information there? Because without even seeing the match, you already knew Argentina is winning. When your friend comes and tells you that, hey, Argentina won today's match, there is not much of surprise for you. There is not much of information for you. You were already expecting this. That is why information content in this case is very low because probability is high. It is a very highly probable event, because of which information content is very low. Now think of the other case. What if that day evening your friend is coming to you and he's saying, do you know India won today's match against Argentinian football team? We won the match. This time there is a lot of information in this because you are taken by surprise. You were thinking Argentina would easily win this, but your friend came to you and told India won the match. So there is a lot of information in this particular statement because the probability was lower. The probability of India winning this match, that was very low, because of which when you got that information, the information content of it is very high. So what did you understand? Whenever an event is a rare event, whenever the probability is very low, information content will be high, and whenever the probability is high, that is if it is a frequent event, information content will be low. This is the point. The reason I explain this is, I want to explain how this formula works. Now you try to substitute in this formula. This is probability. Probability can take values from 0 to 1. This is the case. If you give values from 0 to 1, what happens to log? If you take log, log will map this to an interval from minus infinity to 0. This is what log does. If the value of p of x is very close to 0, log p of x will be very close to minus infinity. That is, it will be a very large negative number. And what if the probability is near to 1? Log p of x will be near to 0. That is, on the negative side it will be near to 0. Now think back. If you are having a very less probable event, you will have log p of x value very close to minus infinity. When you take negative of it, the value will be very high, which means the information content that you have, I of x, that will take a very large positive value when your probability is very low. And whenever your probability is very high, probability value is near to 1, your log p of x will take a value near to 0, which means information content will be less. So this is how this particular formula works, minus log p of x. This is a very good way in order to represent information content. Information content can also be called as surprise. Okay, so surprise is a better way for you to understand that if probability is less, information content will be higher, right? So your surprise or information content is minus log p of x. Next thing you want to understand is, what is entropy? So entropy we dealt in very detail in the entropy lecture. Here I'll give a very small overview. If you want complete details, please check the entropy lecture and come back. Okay, so this is your information content. From this, entropy, this is expected information. You know, this is your information. Expected information is called as entropy. Expected information in the sense expectation of information. Okay, so expected information or expected surprise, this is what you call as entropy. Another way of seeing the same concept is, you can see entropy as the average number of bits required to encode events drawn from P. Let us say you have a distribution P. You can say entropy of this distribution P is the average number of bits that are required in order to encode events that are drawn from P. P is a probability distribution. If you draw events from P and you want to encode those, then what is the average number of bits required? That is what is called as entropy. So both these are different ways of seeing entropy. Again, if you are not very clear about entropy, please go back to the entropy lecture, have full clarity, then come back. Okay, if I explain entropy here again, it will take another 20 minutes. So that's why I am giving a basic idea and we are going to the mathematical formulation. You understood information content, you understood entropy. What I'm going to do is, entropy we generally represent as h of x. So h of x, this can be written as minus sigma, that is sum over all x, p of x into log p of x. So this is how you represent expectation. This is the information. Here I am taking expectation of that information. Okay, it is very simple mathematics. If this is your information, this is expectation. Expectation can be written as sum over all of those probability into that value. That is what I did here. So this is your entropy. So if it is clear till this point, it is very easy for you to understand KL divergence. If you have confusion, please check the entropy lecture and come back, then it will be very clear. So this is entropy. Next thing, whatever I am showing you, this is the entropy considering P as the distribution. That is, P of x is the probability, and here I am trying to understand the average number of bits required to encode the events that are drawn from P, and I am not considering Q at all. Our actual idea of KL divergence, that is based on considering Q in place of P. But here, when I am taking entropy, I am just considering P and I am saying if P is my distribution, then the average number of bits required is this particular value. But one more thing is to be introduced here. Along with entropy, we also have to see something called as cross entropy. What is cross entropy? In case of cross entropy, the expected surprise or the expected value using wrong model Q to encode outcomes from P. This is what cross entropy is giving. That is why it is called as cross. It is cross entropy. What about normal entropy? In that case, it is the expected surprise using P, that is the right model, to encode outcomes from P. That is what is entropy. In case of cross entropy, you are using the wrong model. That is, you are using Q and then you are trying to encode outcomes from P. In that case, what is the average number of bits? That is what cross entropy tells you. What is the formula for cross entropy? In this case, instead of this, it will be sum over all the x, P of x into log Q of x. So this is your cross entropy. We are slowly reaching on to KL divergence. So what does this tell you? This tells you how inefficiently you are encoding the data of P using code that is built for Q. That is what this says. This tells you how inefficiently you are encoding data of P using code built for P. This is the difference, okay? So this is entropy, this is cross entropy. Next thing, how much extra information do we need when using P instead of Q? This is your actual question behind KL divergence. What is your actual question behind KL divergence? That is, how much extra information do you need when using Q instead of P? This is your actual point of KL divergence. How can you mathematically represent that? In order to mathematically represent that, you can say the estimated cost. That is, what did I ask? I asked how much is the extra cost? The extra cost that is required when using Q instead of P. Q in place of P. What is the extra cost? That extra cost can be written as, this can be written as cross entropy minus entropy. So cross entropy, instead of writing CE, I'll use the right notation. Right notation is H of PQ. This is how this can be represented, and this is H of P. This is how I can actually represent entropy and cross entropy. So the extra cost that I have to bear when I'm using Q in place of P, that can be written as cross entropy minus entropy of P. This is the way to represent it. How can you read this? That is, this is the mathematical statement, but how can you understand this? This part tells you when using the wrong model Q, what is the expected surprise or what is the additional information? What is the information? And what about this one? This tells you what is the expected information, or better we'll see in terms of average number of bits. This may be even easier to imagine. Here you can see what is the average number of bits if you are using Q in place of P. And this says what is the average number of bits if you are using P itself in place of P. Then the extra cost is the additional bits that you used because you used Q to represent P. This is the idea, that additional bits is your extra cost. That is what you are going to calculate using KL divergence. This is a better idea, right? In order to imagine, this might be better instead of imagining what is the expected information. Okay. So this says what is the average number of bits required when you are using Q. Then in order to represent how much is the average number of bits, this says when you are using P itself, then what is the average number of bits required? That is to encode events which are drawn from P. In this case, you are using Q. This case, you are using P as the distribution, but you want to always encode the events that are drawn from P itself. Okay, that is the whole point. You want to encode events that are drawn from P only, but the code is written for Q here. Here the code is written for P. This is the difference. Okay. Then what are the additional bits required? That will be cross entropy of P and Q minus entropy of P. How can you calculate this? For this, you can use the above formulas. Cross entropy is this minus summation over all the x P of x into log Q of x minus, what is the formula for entropy? H of P. It is here sigma sum over all the x. So there is a minus in front, I'll put that as well. So this minus is this one. The minus I'm putting inside brackets, that is part of this formula, okay? Sum over all the x, P of x into log P of x. What happens now? When I rewrite this, I'm going to avoid this minus, because this minus and this minus, it becomes plus. So I'll write it in front. Sum over all the x, P of x log P of x minus sum over all the x P of x log Q of x. This is my formula. What am I going to do next? I am going to take the common part outside. Sum over all x, P of x is common. So sum over all x, P of x into log P of x minus log Q of x. And what is the better way to represent? Log A minus log B is log A by B. So instead of writing this, I can write log P of x by Q of x. So this is the KL divergence formula, what we wrote in the beginning. This formula is exactly same as what we derived here. So this is how the logic of KL divergence comes up. So what did we do? We took KL divergence. We saw what is information content. From information content, we understood what is entropy. Then we understood what is cross entropy. Then we understood the extra cost. This is also the KL divergence. KL divergence is cross entropy of P and Q minus entropy of P. Using that, we substituted these formulas. Using that, we found out that sum over all the x, P of x into log P of x by Q of x is the formula for KL divergence. So regarding KL divergence, this is what you want to understand. It is the expected log difference between the true and model predictions. So one you have, that is true and model probabilities. Whatever is the true model probability, you have that. Then you have whatever is the model's predicted probabilities. Then what is the expected difference, the log difference? That is what KL divergence is giving you. So somewhere you can see it as how inefficient is Q. That is, you have P, you have Q. How inefficient is Q when it is compared to the true label P. This is what KL divergence measures. Because of that, you can use KL divergence as a loss function in multi-class classification. So this is what you learned in this lecture. What is KL divergence and what is the purpose of it? How is it used as loss function in multi-class classification? Then we saw the mathematical formulation. Logically, we saw how it is getting derived. And then we saw the complete derivation. One more thing before we conclude this lecture. 2 points I want to emphasize on. 2 properties of KL divergence. So first property, we already discussed these properties. I just want to focus this again. First point is the KL divergence is always greater than or equal to 0. It is always a positive value. Lowest possible value is 0. That is when both distributions are one and the same. Otherwise, it will always be a positive value. Second one is that it is asymmetric. It is not symmetric. That is, KL divergence of Q from P, this is not equal to KL divergence of P from Q. So keep these 2 points in mind. These 2 are the properties of KL divergence.